Okay, welcome back. Let's talk a little bit more about photosystems and pigments with regards to photosynthesis. So, if you recall, plant cells and other producers have chloroplasts, right? And in the chloroplast, we have thylakoid membranes. Well, in these thylakoid membranes is where we have these photosystems for solar energy. So we can think of photosystem as having different pigments, and these pigments are able to absorb specific wavelengths. So they're able to absorb this solar energy at specific wavelength. And so here we have this chart of wavelength here. And so as the wavelengths get longer, you can see they kind of get longer. We're increasing the wavelength, they actually decrease in energy. So the wavelengths that are really short, such as these, actually have a lot of energy. And most wavelengths that we are able to see fall within this sector right here. So this is the visible light that we're able to actually see. So this is the wavelength that we can see here. So we can see that on this side, the wavelengths are a little bit shorter, a little more energy, versus over here at 750, these red wavelengths actually have less energy to them and they're longer wavelengths. You probably recognize some of these other wavelengths, but we can't visually see them. But that doesn't mean that they don't carry energy to them, right? So we have gamma rays and X-ray. This is one of the reasons why you have to wear the whole vest when you go to the dentist, is because these wavelengths are very high energy, right? So we kind of want to protect ourselves. Same thing with UV light. UV light also has higher energy than what we can actually see. They have higher energy than the visible light. And so even though we can't see UV, we can actually feel the energy that radiates off of it, right? And then you have infrared, and actually also radio wave over here, and microwaves. So these all have wavelength associated with them. So let's kind of come back to pigments absorbing specific wavelength. So pigments are able to absorb different wavelength of light energy. So, and whatever they can't absorb, they will actually reflect out. So when I am wearing, for example, a black shirt right now, I'm actually absorbing, or I'm not, my shirt is absorbing all these light energy, but the one energy that is not able to absorb is actually reflected back is black. So it's actually reflecting back black, but it's absorbing all those energy, versus a white shirt. A white shirt is actually absorbing all that light energy, and it's able to absorb every light energy, so it doesn't reflect back any energy in any light too. So that's why it's white. So chlorophyll is the pigment that's able to absorb all the light energy except for green. And that's the reason why plants are green, is because the plants are actually reflecting back the one pigment that they're not, or the one color wavelength that they're not actually able to absorb, and that's green. Okay, so I'll put this video up so that you can take a look at it. This is through your publisher, and it just kind of shows a little bit more about photosynthesis. Okay, so let's look at these pigments and kind of understand them a little bit more. So chlorophyll is the most common photosynthetic pigment, and there's actually two chlorophyll pigments in the thylakoid membrane. There's chlorophyll A and chlorophyll B, and we can actually see them over here. So in this graph right here, what we have is we have the relative amount of absorption to wavelength, right? So here's a wavelength. So here, this is the visible light wavelength right here that we can actually visibly see. And you can see that it's able to absorb all these different colors right here, but it's not really able to absorb green, which is why it's being reflected back. Chlorophyll A and chlorophyll B are here. We also have another pigment that is in the thylakoid membrane that can also harness solar energy. This is also known as a accessory pigment, and we can find it in different photosynthesizer. And normally you don't see We'll look a little bit into season in the next slide, but normally we don't see the output of this pigment because we have so much more chlorophyll that is reflecting green, so we don't really get to see the reflection of the carotenoid. But when do you think you do see them? So if you look at these accessory pigments, you can actually see that they contribute a lot to other color leaves that we actually will observe, such as yellow leaves, orange leaves, or red leaves, right? And this is because they're able to actually absorb light that's in this region right here, in between violet and green. So they're able to absorb those light energy, but they are not able to absorb energy on this end. So they're going to reflect those energies. So they'll actually reflect back your fall leaves color, your yellow colors, your orange color, your red color. And we see them more in the fall, because during the fall with the weather change, the plants are actually going to produce less chlorophyll, so you see less green and you see more of the pigment, the other pigments, the accessory pigments, and the lights that they reflect. Okay, so let's kind of look at the weather and kind of see how the weather contributes to this. So here we have a situation where it's summer, it's really warm, there's a lot of sun energy, the days are longer, so there's so much chlorophyll because the plants want to take advantage of these longer days, and so they're going to produce a lot of chlorophyll, and the chlorophyll is going to allow these leaves, because of the pigments, we're going to be able to absorb so much energy. So much energy gets absorbed, and so we get a lot of green light energy also being reflected out. So all of the leaves look green because they're reflecting all this green light. And so there's so much chlorophyll that we still have the carotenoids making, they're also able to absorb the energy, so they're able to absorb violet and blue and green light, but you can't see the colors that they reflect back because there's so much chlorophyll. So the chlorophyll is just kind of, taking over and not letting the accessory pigment have their day until autumn. Hey, here they are. Now that it is fall, these guys get to be the main character. So now that it's fall, the chlorophylls are not produced as much. The days get a little bit shorter. The weather kind of cools down. There's not as much sun. So, because of the difference in how the sun energy comes down to the atmosphere, we now have the accessory pigment able to play a much bigger role. So now the accessory pigment, which is the carotenoid, can actually go out there and they can absorb the violet. Because remember, that chlorophylls can't absorb green energy, but carotenoid can. So now the carotenoids are going to come out. They're going to be able to absorb the violet and the blue and the green energy, all of the energy that we saw on a shorter wavelength, and they're not able to absorb the red and the orange and the yellow. So while they're absorbing the green, the blue, and the purple, they're able to reflect back the orange and the yellow, and that's why leaves in the fall look yellow to us, because the accessory pigments that are playing a much bigger role in the fall are these carotenoids that reflect yellow through orange, but absorbs more of the blue through violet and greens, right? And so now chlorophyll is not being absorbed as much because just the difference in the daylight hours and weather, chlorophyll is not being produced as much. So now these carotenoids, these accessory pigments, are able to play a much bigger role. In the next video, we'll talk about how we're able to convert all this light energy and carbohydrate into an energy source that the cells really want to use, which is ATP.